Hi, my name is Mirte van der Eyden, and in the following 7 minutes I will introduce our work beyond operator systems that I did together with Gemma de las Coves and Tim Netzer from the University of Innsbruck. Operator systems originate from the field of operator algebra, and they connect to semi-algebraic geometry, convex optimization, and quantum information theory. The central object is the cone of positive semi-definite matrices, the PSD cone, living in a vector space of Hermitian matrices. In this work, we go beyond operator systems. We replace the PSD cone by a general convex cone in a general vector space and define general conic systems. We prove many important theorems about operator systems in this generalized case. In this video, I will explain why we generalize, how we do it, and what our results are. So, why do we go beyond operator systems? Our main motivation comes from quantum theory. The PSD cone plays an important role in quantum theory, since states of particles and effects are modeled as elements from this cone. For physicists, it's still unclear why precisely this cone plays such an important role. In an effort to understand that, people also study alternative theories, called general probabilistic theories, where states and effects are elements from a general convex cone. In order to model multiple particles, one takes a tensor product of these cones. But which tensor product? For the PSD cone, there exists a tensor product such that two PSD cones become one larger PSD cone again. Therefore, the composition of two quantum states gives again a quantum state from the larger PSD cone. This tensor product is very special. For general cones, such a tensor product is not known. Apart from the minimal and maximal tensor products between general cones are still poorly understood. We would like to understand this better and use operator systems to answer the current open problems about tensor products of cones. But the framework of abstract operator systems, as it is too narrow to tackle these problems. So we go beyond operator systems. But first, what are operator systems and why should we use them to solve these open problems on tensor products? An operator system on a real vector space X is an infinite family of convex cones. At every level S, there is a vector space X tensor the Hermitian matrices of size S, and we choose a full-dimensional convex cone inside all these spaces. These cones have to be compatible under certain relations, in this case matrix contractions. When contracting an element from the cone at level 3, for example, with rectangular 3x4 matrices, we should end up with an element of the cone at level 4. One consequence of this definition is that on top of every convex cone at the lowest level, here the yellow cone, there is a smallest and a largest way to extend this cone to an operator system at all levels. The smallest operator system is given by the minimal tensor product between the yellow base cone and the PSD cone of the corresponding size. Dually, the largest operator system is given by the maximal tensor product between these cones. Every other operator system should be in between these options at every level. The reason that the green PSD cone plays this important role is a direct consequence of the imposed relations between the levels, the matrix contractions, and the vector spaces. So everything that's green in the left picture. We can view an abstract operator system as a uniform tensor product between a base cone and a PSD cone. With this I mean that choosing all the cones of the abstract operator system is equivalent to choosing a tensor product of the yellow cone with the PSD cone of all sizes simultaneously. But instead of tensor products with the PSD cone, we are interested in tensor products between general convex cones. So we go beyond operator systems and generalize them. Now, how do we do that? A general conic system on a vector space X is still a family of cones. But instead of vector spaces of Hermitian matrices, we can choose different vector spaces and different relations between the levels. So what we change is the underlying structure. For example, we can choose as these vector spaces all possible vector spaces, not just the Hermitian matrices, and as these relations all the possible linear maps. This leads to what we call vector systems, but there are many more options. What the options have in common is that the levels should come from elements in a category with some nice properties, namely it is star autonomous. The objects in this category become the levels, and a functor from this category to the category of vector spaces picks out the vector spaces and the relations between them. For example, the arrow between the object C and 1 here in the category will result in a linear map between the level C and the level 1 under which the cones have to be compatible. Now, what do we gain by this generalization? We prove that many important theorems about operator systems remain true for general conic systems. For example, the Choi-Krauss representation, Choi-Everos realization theorem, Arvidson's extension theorem, and many more. By applying these theorems to the different choices for the underlying structures, we recover existing and find new results. For example, applying the generalized version of Arvidson's extension theorem to the vector systems exactly gives us the homomorphism theorem for vector spaces. For simplex systems, operator systems and cone systems, all arising from other underlying structures, we recover Farca's lemma, Arvidson's extension theorem and Rutz's extension theorem, all well-known results. But we also find new results. Applying it to even more examples, such as group representations and unitary representations, gives rise to extension theorems that were previously unknown. We believe that with general conic systems, we unlock the full power of operator systems. If you want to learn more, please have a look at our paper. The link is in the description. There you also find a link to a 25-minute talk about the same work, which goes into a bit more detail. Thanks a lot for watching.